The steady state operation in switching converters is defined slightly different from the conventional definition of steady state in non-switching circuits. So in this video, we will define the DC steady state as applied to switch mode power converters and look at its significance and also go through two simulation examples that distinguish between steady state operation and transient operation. So first of all, why do we care about DC steady state operation? The reason is the DC steady state analysis can be very useful for first thing is to understand the basic operation of different types, different topologies of power converters, all the way up to the analysis in each sub-interval and different operating modes. Then when you say you want to understand the operation of a power converter, one of the most important things that you should be able to do is to derive the input-output relationship in terms of the control variables such as duty ratio. And this is facilitated by the DC steady state analysis for DC to DC converters. Then the design of various components, particularly the design of the filter components such as inductors and capacitors, and if it is an isolated DC-DC converter, the design of transformers, all of those are facilitated by a thorough DC steady-state analysis. And even the selection of the voltage rating, current ratings of the various power semiconductor devices like the MOSFETs and diodes, that is also done by doing a steady-state analysis. And finally, it is also useful in determining the losses in various components and in doing a design trade-off in order to, for example, optimize the efficiency. So let's first look at the definition of DC steady state in non-switching circuits. So as an example, I'm showing this LCR circuit, LC and two resistances. And this LCR circuit is excited with a DC voltage source of 100 volts at t equals 0. So the response, I obtained that directly from simulation. So I'm showing the two state variables, namely the inductor current and the capacitor voltage. So if you focus on the inductor current, it goes through an initial oscillation, a damped oscillation, corresponding to the damped natural frequency of this LCR circuit. And eventually it reaches a constant value, looks like around 2 amperes or so. Similarly, if you look at the capacitor voltage, also rises. It goes through the same damped oscillations, and again eventually reaches a constant value, slightly less than the applied 100 volts. So we would define this region, this shaded region, as the transient portion of this operation. So that is when both the inductor current as well as the capacitor voltage, they are time varying, their magnitudes keeps changing, they are oscillating. And this region shaded in a different color, a blue color, so that is the region after t equals 0.6 seconds. So that is called as the steady state, or a DC steady state in this case. And here you can see both the current as well as the capacitor, they have constant values. So therefore we can define in non-switching circuits the DC steady state as a condition when all the variables, so I've shown only two waveforms, inductor current, capacitor voltage. If you look at any other waveform, for example the voltage across any of these resistances, they would go through oscillations initially and eventually reach a constant non-varying value. That is when we say the circuit has reached the steady state. Okay, so the definition for non-switching circuit is a condition when all the variables, all the voltages and currents, they are constant in time invariant. Okay? The instantaneous quantities are constant. Now, since in DC steady state, all the quantities are constant, therefore their derivative would be 0. Okay? So in particular, the current voltage relationship for an inductor is VL equals L dIL over dt. And since IL has to be a constant instantaneously in DC steady state for non-switching circuits, its derivative should be 0. Therefore, the voltage across the inductor in DC steady state, even instantaneously, is 0. Okay. So once you have the voltage is 0, then you can replace the inductor by a short circuit because the voltage is always 0. Okay. Therefore, I'm sure you must have seen this several times before. In DC steady state, for non-switching circuits, the inductor can actually be replaced by a short circuit for DC analysis. Okay. Similarly, for the capacitor, just the dual, since IC is C dV over dt and VC has to be a constant, therefore its derivative is 0, or the capacitor current is 0. So once you have a 0 current in a component, then that is as good as an open circuit. Therefore, again, as you may have seen several times before, in DC steady state for non-switching circuits, the capacitor can be taken out. It can be replaced by an open circuit for DC analysis. Now, coming to the switching converters, we see a big difference. Now, in switching converters, even in steady state, most of the quantities, most of the voltages and currents are either switching waveforms or at least they are time varying. So I'm showing two examples. In any converter, this pole output voltage would be a switching waveform. It is equal to the V sub D when the switch is on, and it's equal to 0 when Q signal is 0. So it's always a switching waveform. The pole current or the inductor current, even though it is not a switching waveform, but it is also time varying, and this is whether it is in transient or steady state, the switching and time varying inductor current is always happening. So therefore, we need to come up with a different definition for DC steady state in switching converters. The definition that all the quantities are time invariant or they're all constant does not hold good for switching converters because they are always switching. So the definition for DC steady state in switching converters is shown here. Actually, there are, I will say this in two different forms. This slide has the first form of the definition. It says that a switching converter is in DC steady state if all the waveforms, so every current and voltage, all those waveforms, they repeat exactly every switching period. Okay, so they repeat cycle after cycle. They have the same wave shape, same amplitude from one cycle, going from one cycle to the next cycle. Or mathematically, for example, the current, the pole current IA at any time t is exactly same as the same current at t equals t minus one switching period ts. Same thing for all the other voltages and currents as well. As an example, here are the two waveforms of the pole output voltage and the inductor current, and this is in steady state because by our definition, if you look at what happens, for example, this V sub A, so let's say this is 1 point here. Okay, this is equal value of 100 volts and exactly one cycle after that. So that would be at this point. So this is one period Ts. Okay. So the waveform at one switching period later is exactly the same value. Therefore, this waveform is certainly in steady state. And if you look at the inductor current, again, at the same time, it has a value of here, and one switching period later, it has exactly the same value. Okay. You can look at any point, and Ts seconds later, it will have the same exact magnitude, same value. Okay. Therefore, both the V sub A waveform and IL waveform, they obey this definition. Therefore, the circuit is in DC steady state. Okay. One key point to note is that the definition requires all the waveforms. Okay. So it is possible in a circuit that V sub A has this obeys this expression, but some other quantities like the inductor current may be either increasing or decreasing. Then the circuit is not in steady state. Okay, so we require all the waveforms to have this property. And this is an example of a non-steady state or a transient condition. Clearly, you can see that both V sub A and IL, they violate this condition. Okay, so you can see that the duty ratio of V sub A is constantly increasing, and similarly the inductor current is also continuously increasing. Therefore, the value at a given time is not exactly the same as the value one period before or one period after. So this is the second form of the definition of DC steady state in switching converters. Obviously, the concept is the same as what I showed in the previous slide, the form 1, but this is easier to apply, and it is also similar to how we defined the DC steady state in non-switching converters. So the statement is a switching converter is in DC steady state if the cycle by cycle average values of all the variables remain constant. So the key difference between non-switching and the switching is the CCA value here. In a non-switching converter, even the instantaneous values were constant, whereas in switching converters, instantaneous values can be switching or time varying, but if we take their average over one switching period, the CCA values, they remain constant if the circuit is in DC steady state. Example is same as before, the pole output voltage and the inductor current, and these are in steady state. The only difference is now I have also added the cycle by cycle value of each of these two waveforms. So clearly, vis-a-vis average, this red waveform is a constant, therefore this is in steady state. Similarly, the inductor current, its average value is this red line. Again, this is a constant over time, therefore this circuit is in steady state. An example of a transient non-steady state condition. Here both vis-a-vis and IL, they are their cycle by cycle average, the red waveforms in both the plots, they are both increasing. Therefore, it is a non-steady state condition. Next, I'm going to show a simulation of both the basic non-switching circuit here, the RLC circuit, and here is the switching converter, which basically has the same circuit, only the input, instead of applying it as 100 volts DC source, I'm applying an average of 100 volts by switching from 200 volts DC source at a duty ratio of 0.5 in this power pole. So this part of the circuit is identical to this part of the circuit, and only the voltage that appears here, instead of being 100 volts instantaneous, it is a 200 volts to 0 switching waveform with its average equal to 100 volts. So here are the simulation results. This particular one corresponds to the waveforms from the non-switching RLC circuit. The first one is the applied DC voltage at t equals 0. It's given as a step of 100 volts, remains constant at 100. And the second one is actually the inductor current waveform. It goes through this undamped transient oscillation and reaches steady state after around 0.6 seconds. So this value here, inductor current, settles down at a value slightly below 5 amperes, and that is steady state. Similarly, the last waveform is the capacitor voltage. After an initial oscillation, it eventually settles down at a value slightly below 100 volts, and so after 0.6 seconds, all the waveforms are constant. Therefore, we can say that the circuit reaches steady state after 0.6 seconds. Okay, then these are the waveforms from the switching converter of the same simulation example. Again, you can see that, so the first waveform is the pole output voltage. I'm also showing its cycle by cycle average value, which is this red waveform, and you can see that is clearly 100 volts. Okay, it is the instantaneous waveform is switching between 200 and 0, but the CCA value is constant at 100 volts, okay, throughout. Whereas the second plot, which is the inductor current and its cycle by cycle average shown in red, you can see that the inductor current is always time varying. Okay? It has a high frequency component, but the cycle by cycle average value settles down after about 0.6 seconds. It is not changing anymore. Okay? Initially, it is changing, but after 0.6 seconds, it remains constant, just a cycle by cycle value. Similarly, the last waveform is the capacitor voltage from the switching circuit, and again you can see that both the instantaneous as well as the average values become constant after 0.6 seconds. So this switching converter can be said to be in DC steady state after 0.6 seconds, because each one of these three waveforms, their cycle by cycle average values remain constant. Now in the second simulation example shown here, I want to illustrate the transient due to a step change in the command in the reference of a closed loop controlled step down converter in this case. So this is the output voltage is being regulated. Initially I give a reference of 15 volts, and then at 4 milliseconds I change the reference to 18 volts, and so it will reach steady state at 15 volts initially, and after this change in the command, it enters a transient condition and eventually reaches a new steady state. So that's what we're going to look at. Simulation start. So the converter went through an initial startup transient. The inductor current rises from 0 and eventually reaches the final value. Similarly, the capacitor voltage also reaches 15 volts as per the initial command. So this region is the startup transient region. This is the steady state, and at t equals 0.4 millisecond, I'm applying, or maybe 4 millisecond, I'm applying a step change in the command from 15 to 18 volts, and you can see the top waveform is the pole output voltage. If I zoom in near this transient, so you can see the switching pulses, and you can see the variation in the duty ratio also. And the red waveform is a cycle by cycle average of the pole output voltage. So it goes through a transient. Similarly, a transient in the inductor current as well as in the output load voltage. And eventually, I should zoom back, somewhere after probably 0.5 seconds or maybe 0.55 seconds, you can see each of the three cycle by cycle average waveforms in VA, IL, and the output voltage. They remain constant, and they have now reached a new steady state corresponding to an 18 volts output. Okay, a few more points about the DC steady state in non-switching circuits versus switching circuits. So we already seen that in a non-switching circuit, the definition of DC steady state is all the instantaneous quantities in voltages and currents, they are constant, time invariant. Whereas in switching circuits, all the quantities are time varying. They are most of them are switching, but their cycle by cycle average values, they are constant in DC steady state. So because of this fact that all the quantities are instantaneously constant in a non-switching circuit, any derivative is 0. Therefore, the voltage across the inductor, which is L dI over dt, is 0. Therefore, we can replace the inductor by a short circuit for DC analysis, and the actual value of L has no impact on the DC analysis in steady state. Whereas in the switching circuit, even though the average voltage across the inductor is 0, the instantaneous value is not 0, and the value of inductance does have an impact. That impact is on the switching frequency current ripple, even in DC steady state. Okay. So in later videos, we will be learning in much more detail this concept where the average voltage is 0. We'll call that as volt-second balance principle. Okay, and similarly, the capacitors are dual. So the instantaneous current through a capacitor in non-switching circuit is 0 in DC steady state, and it can be considered as open circuit because the current, which is dV over dt, is 0. In the switching circuits, the average current through a capacitor is 0, and but the instantaneous current is not 0, and the value of the capacitance determines the amount of switching frequency ripple in the voltage of the capacitor. Okay, let's conclude this video by discussing briefly about the AC steady state. So this video has focused on DC steady state, whereas when we get to study of DC-AC converters or AC to DC converters, then we will be dealing with AC steady state as well. Okay, in AC steady state, even the cycle by cycle average quantities will not be constant. So they can be constant, or more likely there will be some fundamental frequency component, or sometimes it can also be multiple of this fundamental frequency. So the fundamental frequency itself is going to be significantly lower than the switching frequency. One example would be like the grid interface of renewable energy resources. There it's a DC to AC inverter where the fundamental frequency is a grid frequency at 60 Hz, and to realize that we will be switching at frequencies in the order of tens of kilohertz. So the switching frequency is much larger than the fundamental frequency. And once the circuit reaches AC steady state, then all the voltages and currents would have either the most likely the fundamental frequency. Some of them may have like twice the line frequency, and some of them may be just constant values. And the fundamental frequency components, once they are in steady state, they will have the same amplitude and same phase going from one fundamental cycle to the next. And as I mentioned, this is very useful in analyzing DC to AC converters or AC to DC converters.